Hello, hello, hello. This is Nicholas, and I'm going to be doing a video on what's known as variation of parameters for solving ordinary differential equations. And variation of parameters works with a much broader class of second-order linear differential equations than the method of undetermined coefficients. It can actually solve provided, there's later on, you'll see we're going to have to do some integrals, and provided that all the integrals actually have antiderivatives, then it can solve any differential equation of the form ay double prime plus by prime plus cy equals any function of t on the right side. So not just limited to sine, cosine, e, and power functions. So the solution is going to be found the same way that we did with the undetermined coefficients. We're going to find a particular solution to this, and we're going to find y sub h, the homogeneous solution, when f of t equals just 0. So the trick, I guess, so to say, is for finding the y sub p. And we're going to assume that y sub p can be written in the form before that, let's say that the solutions to this differential equation, the fundamental set of solutions, is, say, y sub 1 and y sub 2. So like in the last video, the homogeneous solution was c sub 1 e to the negative 2x plus c sub 2 e to the negative x. So your fundamental solution set there would be e to the negative 2x and e to the negative x. So let's call that fundamental solution set y sub 1 and y sub 2. Then we're going to assume that y sub p can be written in the form v sub 1 v sub 1 y sub 1 plus v sub 2 y sub 2, where v is some other unknown function of t that we're going to try and find. So if I were to differentiate this, I'm going to have to do it twice. I have to use product rule twice as well. That's v sub 1 y sub 1 prime plus v sub 1 prime y sub 1 plus v sub 2 y sub 2 prime plus v sub 2 prime y sub 2. And to make computations a little easier, I'm going to impose this first condition. And this is just something you got to know. I guess you could derive it later. I'm going to assume that v sub 1 prime y sub 1 plus v sub 2 prime y sub 2 is, so v sub 1 prime y sub 1 plus v sub 2 prime y sub 2 is 0. And I'm doing that to make my computations easier, so that I don't have all, here I would have to use, when I differentiate again, I would have to use 4 product rules, and then I would, it would explode in complexity. So we impose that condition to make our computations easier. So now y sub p prime is just v sub 1 y sub 1 prime plus v sub 2 y sub 2 prime. Now the second derivative is v sub 1 y sub 1 double prime plus v sub 1 prime y sub 1 prime plus v sub 2 y sub 2 double prime plus v sub 2 prime y sub 2 prime. Okay. And I'm not going to impose any conditions here quite yet, but what I'm going to do now is plug in this and the first derivative into our original equation. So a times v sub 1 y sub 1 double prime plus v sub 1 prime y sub 1 prime plus, I forgot a plus v sub 2 y sub 2 double prime plus v sub 2 prime y sub 2 prime plus b times, this one isn't quite as bad, v sub 1 y sub 1 prime plus v sub 2 y sub 2 prime plus c times v sub 1 y sub 1 plus v sub 2 y sub 2. And all of that good stuff is f of t. So, how can we clean this up? I want to mess with stuff algebraically so that I can get some zeros in here. In other words, I want some ay sub 1 double prime plus by sub 1 prime plus cy sub 1, because that's going to be equal to 0 because we assumed it to be so up here. So I have v sub 1 times, now I have a y sub 1 double prime plus by sub 1 prime from here plus cy sub 1. Now I have plus v sub 2. Now I have the y double prime here, so ay double prime plus, now I have the by prime here plus by prime plus, now I have the c. Oh, I forgot my two. There we go. Plus the c y sub 2 there. And now what isn't underlined? Oh, well, I use this one too. So plus a times v sub 1 prime y sub 1 prime plus v sub 2 prime y sub 2 prime. That's all equal to f of t. Now look at this. This is pretty nice, actually. This is 0. This is 0 because y sub 1 and y sub 2 are solutions to the homogeneous equation. We assume them to be solutions to ay double prime plus by prime plus cy equals 0. So when we plug in y sub 1 and y sub 2, we're going to get 0 because they're solutions. So that's gone, that's gone. So that means f of t over a is v sub 1 prime y sub 1 prime plus v sub 2 prime y sub 2 prime. And this is the second condition and the only other one, at least for second order equations, that I'm going to impose. So that is really all the derivation for variation of parameters. So, just remember your two conditions. So, and I'm going to write them up here. Condition 1 is that v sub 1 prime y sub 1? Yeah. V sub 1 prime y sub 1 plus v sub 2 prime y sub 2, that's equal to 0. And our second condition is that v sub 1 prime y sub 1 prime plus v sub 2 prime, there's a prime there, y sub 2 prime, that's got to be f of t over a. So let's work through an example. This is a pretty classic example. Let's do y double prime plus y prime, or plus just y, is equal to the tangent of t. Now notice, though, that the method of undetermined coefficients could not solve this, but variation of parameters can. Because undetermined coefficients, when we differentiate tangent, we would be getting a secant squared and then a 2 secant cubed tangent, and so there isn't any predictable pattern in the derivatives of tangent. That's why we need the variation of parameters here. So what are our two? Well, first we should find the homogeneous solution. So y double prime plus y prime equals 0, or r squared plus 1 equals 0, and r is equal to plus or minus I. So our homogeneous solution is just c sub 1 cosine x, or t, plus c sub 2 sine t. So our fundamental solution set is cosine of t, sine of t. And I'm going to let cosine of t be y sub 1 and sine of t be y sub 2. Now that we have that, that tells us that v sub 1 prime times y sub 1, which is cosine of t, plus v sub 2 prime times the sine of t is 0, and v sub 1 negative v sub 1 prime times the sine of t, because when I differentiate cosine I get a negative sign, plus v sub 2 prime times the cosine of t, because when I differentiate sine I get cosine. That's going to be f of t, which is tangent of t, over a, and a is 1 because this is 1 right here. So now we just need to, this is just systems of equations, so now we need to, we can substitute, eliminate, however you want to go about solving that. I think I'm going to multiply this by a sine of t and this by a cosine of t. So v sub 1 prime sine t cosine t plus v sub 2 prime sine squared of t is 0, and negative v sub 1 prime sine t cosine of t plus v sub 2 prime cosine squared of t is sine of t. Tangent times cosine is sine. I'm going to add these together. That's gone. And now look at this. When I have v sub 2 prime times sine squared plus cosine squared, that just gives me a 1. So v sub 2 prime is just sine of t. And so v sub 2 is negative cosine of t. So now we can go back and find what v sub 1 is. Because I know originally from this equation here, I know that v sub 1 prime cosine of t plus v sub 2 prime, which we found to be sine of t, so that we get plus sine squared t, is 0. Or in other words, v sub 1 prime is negative sine squared t over the cosine of t. And that's, normally sine squared t is 1 minus cosine squared. We have the negative, so that makes it cosine squared t minus 1 over cosine of t, which is cosine of t minus secant of t. So v sub 1 is, when we integrate, that's sine of t minus natural log absolute value of secant t plus tangent t. So our y sub p we assume to be in the form v sub 1 y sub 1 plus v sub 2 y sub 2. So our v sub 1 is this good stuff, and our y sub 1 was cosine of t. So that's sine t cosine t minus cosine of t natural log absolute value secant t plus tangent of t. And now we add v sub 2, which is just negative cosine t, times y sub 2, which is sine t, so that's minus sine t cosine t. That and that cancel out. And so our y sub p is just this. That means our most general solution is y sub h plus y sub p, which is c sub 1 cosine of t plus c sub 2 sine of t minus cosine of t natural log absolute value secant of t plus tangent of t. And we are done. That is the answer to that differential equation. and that's really a nice one.